Okay friends, so welcome to the last lecture on cache memory. So today we'll be discussing certain things, what we have not covered till date regarding the cache memory. So uh, there'll be a couple of things, couple of factors that affects the performance of cache memory, to be precise. So for that, again, you can follow this one, reference number 1, or if you wish you can also have a look in the reference number 2. Now before we start today's session, because today will be a short session, so before we start, let us see where we are, right, as far as the cache memory discussion is concerned. So we have started our journey we have given an introduction, right, and a good motivation regarding the cache memory, and what was basically the speed gap, right? The speed gap between the processor and the main memory is wider, right? And as the day progresses, the gap between the processor, or the performance gap between the processor and memory is getting wider and wider. And so there is a requirement to place something in between, and that something is nothing but our cache memory, right? So which happens to be faster than the memory, and this processor and main memory is again coming from our von Neumann or stored program architecture concept, right? Okay, and so it was not only the speed limit, right? As we have seen that we bring things to the cache, right, as far as processor's request, right? Now let's say if you want to see a bit more, so there is a so we have our processor. So processor will request for one word using some address, let's say 100110, right, some address. Now this will be brought from the main memory if it is not there in the cache. So it will be brought from the main memory to the cache. Now while bringing things from main memory, we have seen that we will not be bringing only one word, rather we'll be bringing a couple of words, and that is nothing but a block, right? And we have seen we have rather solved many problems on that a block contains many words, so we'll bring many words to the cache. So essentially the locality of reference was to use the broad blocks, whatever words in a block. Suppose I bring a particular block, say I, so this block will contain several words, right? And processor might have requested only for this word maybe, right? So there is a huge probability that it will in the near future it will be requesting these blocks, right? So that was the spatial locality in terms of space, right? So that was one motivation of our the cache memory. And another one was the temporal. So temporal one, you bring this word, so there is a high probability that the processor will again after some time request for this particular word having address 100110. So that is all about locality of reference, right? Okay, so that was basic motivation behind using cache. And then we have seen the overall functioning of the cache memory. We have what happens in case of a request. Then we have seen different types of mappings, how a line in cache line is associated with a memory block, main memory block, right? So direct, there's a 1-to-1, one memory block can go to only one cache line, or one cache line contains only things from our dedicated memory blocks, right? Then we have seen associative. where each a block in main memory can go to any line in the cache. Then we saw set associative, something in between, which can go to a set. Now then we have seen the replacement policies, right? A couple of replacement policies, FIFO, LRU, least recently used replacement policy, then NRU, not recently used. And then we have also talked about optimal policy, what is the best possible situation or scenario we want, right? Then we have seen things from performance of cache memory, right? What do you mean by performance? And that was basically measured in terms of average memory access time, which happens to be hit time plus miss rate into miss penalty. So that these are the things we have already seen. Now coming to today's discussion, see, till now what we have seen is essentially those were mainly read requests, right? So just now what we have said here, that the processor wants to read some data, it wants some data from this memory location. So typically we assumed that it was a read request, right? Now there are certain differences between read request and write request, right? And what do you think? The number of read and number of write request from a processor to the memory, will it be same or it will differ? Well, if you recall the pipelining concept we saw, or the phases of an instruction, we saw that it consists of, again, fetch, decode, execute or ALU, memory, write back. So all the instructions are fetched or need to be read from memory, right? So that is one of the things. Then second point is, we have also seen that every instruction doesn't produce some result, right? Some result to be written in memory, it doesn't produce, right? So naturally, number of reads happens to be more than number of writes, right? Okay. Now read can be faster than write. Now to make that thing, to understand that, let us come to this place. Let's say again we have a CPU, right? So it requests for some data, right? From some memory location, and it specifies some address, right? The address contains some 100 something, like 110, whatever. Now out of that address, we know that few things will be tag, few will be set and block or word, right? Okay. Now what happens? So it comes to the, so remember we are here, right? Okay. So suppose we want to read something, it's a read request, then it should be seen in the cache. Let's say it's a direct mapping to make the thing simple. That means you will have some place in the cache with these, with this address. Let's say the place is this. So the first part is tag and the address, the data. Now then, suppose it is there. This word is, word is there. So that means, even if it is there, we have seen, even if it is there in the cache, so this word might not be the word it is requested for, right? Because this block, even if in case of direct mapping, if this happens to be my main memory, then this block might be filled with this block, or it might be filled with some other block, right? Because we have seen that a particular block in cache can be filled with many blocks, right, from the main memory. Now to check whether, suppose it requests for this particular block. Now to check whether this block is this or this, what you need to do, it needs to do a tag comparison, because this block will also have some tag value. Let's say this is 10 whatever. So we need to do a tag comparison here, so as to be ensure that whether the requested block is this one or the requested block is this one or this one, right? So this is done in tag comparison. Now what can be done here is what people does, that this reading, after all, what is to be done? After all, once this business is done, whatever is there, this is to be given to the CPU, right? So this is actually our read request, reading the content of this particular word, rather a word from this block. Now what it can be done, that this tag comparison and this reading from these things, right, these things can be done in parallel, right, in case of read. But in case of write, this cannot be done in parallel. So in case of read, let's say you might think that, okay, we said that this block might be this block or this block, but this is done to save some time, right? So just some aggressive approach. If the reading block happens to be the actual block requested for, we have a good luck. That's good. Even if it is not there, then we'll simply ignore whatever we have read from the cache. That can be ignored. But the same thing cannot be done in case of write, because write particularly specifies a block. So you cannot start writing this in this particular the block rather item over here if there is a request for this. There will be a you can imagine what kind of problem it will lead to, right? So simply that's not possible. So that means the read can be made faster than write, right? And the logic is that the block read and the tag comparison can be done in parallel, right? And then there are certain write policies. We'll see we will see two types of write policies. One is write through, another one is write back, right? And remember that the cache memory contains only some portion of the main memory content, right? Because whatever is there, there's a communication is happening between processor and main memory, right? And the cache is coming in between so as to help the communication, so as to make the communication faster. And the cache contains a portion of the main memory content, right? And if there is a write, in case of read, the life is simpler. But in case if there is a write, what do you want? We want the communication, that the write communication should reach to main memory, right? Because the content is there in the main memory. So whatever content we're dealing with in cache, that contains basically belongs to the main memory for our discussion, right? So we need some way for this communication to be established, to be there. How if you change something in cache, how the changes will be reflected to the main memory. That's what the policy talks about. And of course, each policy will have its individual merits and demerits. We'll see some of them. So write through says, you write throughout. It's a through, right? So through to the next level. So it says information is written, or whatever we want to write, that is to be written both in the cache. So of course it is to be written in the cache at any case, and it is also to be written in the main memory. Or if you have multiple layers of cache, then it is also to be written in the next level of cache, right? Okay. Now if that is the case, so the positive point is, this is a positive point, is that main memory contains the updated data. right? So you will, though we are discussing a single processor system, now you can imagine that you have a multi-processor system, right? Many processors are requesting data, right? Or other, there's a demand coming from many places, processors and co-processors. Then what will happen, right? If you don't have the updated data, so you can think the importance of data to be updated. So that's a positive point in case of write through, right? And if that is the case, what is the negative point? One of the negative point is this one, that it generates more traffic in the sense more packets in the network, or more request with the updated information. So essentially it consumes more memory bandwidth, right? On the other hand, if you have a write back memory, so here what is done, information is written only to the cache, and the main memory will be updated when the block is replaced, right? So we know what does block replacement policy means. Block replacement means, right? So whenever block is replaced, so it will be so whatever changes we do in the cache, so that is to be updated, right? So it is like, so we have the cache. If you change something here, right? So when this block will go to the main memory, it will be updated, right? And of course, not all the blocks need to be updated. We can update only the modified blocks. So if you remember, we said that there will be a bit called dirty bit or modified bit, right? So that will say whether the block is, we did any changes in the block or not. And suppose we do, let's say we often do, right? Say we have a those doesn't fit for a one variable. Let's say we change some, suppose the content is 5 right now, one variable content, let's say it is getting stored in some memory location A200 whatever, right, is currently 5. Now the program changes it to some 7, right? After some time the program changes it to some 9, right? Now imagine that we are using cache, write through cache. So this 7 is to be updated to the cache. Again, then you are changing, so 9 is to be updated in the cache, right? Because we are modifying. So, but essentially, what we need the, right? If we can maintain that there is, only the 9 is essentially updated. The updated value is 9, right? This 7 is getting lost somehow. So then we don't need to make a write request every time. So we can combine these writes and we can make a single write, right, with the latest value, right? So that thing, of course, this cannot be done in all the, in every situation. There are some TNCs are there, but to make the thing simple, suppose if this is the scenario, then that we are changing it quite often, and then if we are using write back policy, then we can do that, right? We can combine all these writes and we can make only one write over here to the main memory, right? So that's what is written over this statement, that one write to main memory in case of repeated writes, right? Okay. Now let's see what happens in case of a cache miss. Cache miss and a write happens, right? So there are two ways to handle that. One is write allocate, and another one is no write allocate. So it means, right, simple. So we have the cache, right, the CPU and main memory. So the point is, in case of write allocate, a request happens and you allocate the data to the cache. Now remember, we have drawn this kind of diagram So that was typically meant for our read, right? Because read happens this way only. But in case of write, you need to, it generates a request with some address, right? So in write, no write allocate, you won't be allocating this particular, block containing this particular word to the cache, right? In case of write allocate, you will be allocating to the cache. This is no write allocate. So you are directly modifying over here, right? So this is one approach. The no write allocate is another approach. Again, of course, there will be merits and demerits. Now, in no write allocate, modification is done only in the main memory, right, or in the next level of memory, whatever with respect to the concerned level of cache, and the block is not kept in cache, right? Now, just few minutes before in the last slide, we saw that whether we want to go for write through or write back. Now we have seen that again in case of write miss, we have two options: write allocate, no write allocate. Now which one will be linked with which one? Write through with write allocate or no write allocate, or the other way around. Essentially, it can be done in any way. Write back and write allocate can be clubbed together. Write back, write no allocate can be clubbed together. But this is a typical combination. With that, what we do, that the write back is combined with write allocate. See, what happens in case of write back is that you will gather many write requests and will go to the main memory once. If that is the case, then you can put this, put the cache block, put the block to the cache, and thinking that there will be subsequent write. So in case of subsequent write, you don't need to go to the main memory to bring the block. So you are allocating here, so you can do the modification here, right? And then you can combine, and whenever the block is replaced, you can make the write. On the other way, in write through, anyway you are always going to the write request always goes to the main memory, right? So it traverses all the way. If that is the case, anyway you are traversing all the way, then why you keep the block over here? No need to keep the block to the cache, because anyway the traffic goes till the main memory. Your request will go to the main memory, right? So that's what the motivation behind using these combinations this way, right? Okay, now to make this policy, to understand this policy a bit more, let us say we are given this scenario. There is a write request, memory write request from CPU with this memory address, say A124. Now we want to see what happens if we go for write allocate policy, whether it's a hit or miss, and what will happen in case of no write allocate policy if there is a hit, whether there will be hit or miss, right? If these requests are generated one after another. Right? So initially, let's assume that the content of these blocks are not present in the cache. So if that is the case, you can try by yourself, or rather, let me put it here. Since this is a request for the first time, so no matter whatever policy you apply, there will be a miss, right? And then there is a read request to the same block, right? And now you are using write allocate. Since you are using write allocate, you are allocating the block to the cache. So that means the subsequent one will be hit. But if you don't allocate, it will be miss. Simple. Right? Same is the case for, let's say, another address. Initially, both will be miss. Whatever you do, you need to bring it to the cache. That's a miss. Then again another write request comes to the same, containing this address, so containing the same block. Since we are doing we are allocating the block to the cache, that will be a hit, right? And if you go for no write allocate, so we are not allocating anything, so that's a miss, right? So this is just to make make things clear regarding the write miss policies, right? Okay. Now moving ahead,